issue.
Sorry to interrupt, but we don't see the slides.
Yeah, but you're not interrupted.
Sorry. Classic mistake. Now you can, right?
Yes, thanks.
Very good. Let me just hide this one. 1 second. Hide video panel. Floating. Okay, great. Try Lorenzo. Does it work?
Yes.
Perfect. Okay, sorry.
All right. Okay, so today I'm going to talk about maybe not.
No, again.
No, so okay, no, I can, but it doesn't go up.
It doesn't.
It doesn't. Yeah.
Oh God. Try now.
Okay, now it
Yeah.
does work.
So I'll stay here for a second, but you continue.
Okay, so this is the work that I wanted to talk to you about today. So it is a simple work, I think, but the reason why I decided to discuss this one is that I think touches upon many topics which are timely and of interest in the recent literature today, and also I think overlaps with a few different topics of interest in the group. But also, so since this is rather narrow work, I also wanted to mention that I have a few interests. I've been working on a few things recently. So these are a few keywords that describe projects I'm doing this day. So if you resonate with one of these, I'll be here until Friday, and I would be very happy to discuss. Okay, so let me start with a perhaps too broad contextualization. But I think it's fair to say that one of the early motivations of this type of research was really to try to understand questions of thermalizations of macroscopic systems based on quantum mechanics. And of course, it's been a long time since we had a microscopic theory for thermalization, for thermal equilibrium given by Gibbs. But even Gibbs himself realized that his theory is actually not a microscopic theory in the sense that it is based on some postulates that are not easily derived from a more fundamental microscopic theory. And so in the past, I would say 20 years, there's been a lot of work in progress into try to actually deriving some of these postulates by essentially getting around the difficult problem of describing an interaction between a system and environment and study the question of thermalization in isolated many-body quantum systems. And so one of the motivations for this kind of research, which might seem a bit strange at the beginning, I think an important motivation came from the physics of ultra-cold atoms in the early 2000s. And so these systems are nowadays routinely realized in labs and essentially consist in mesoscopic numbers of atoms, which you can think of really elementary quantum degrees of freedom, which interact with one another and allow you to construct theoretical models to a high precision and probe their non-equilibrium dynamics. So this gave a boost to the community, the theoretical community, to try to pick up against this problem and try to make some progress. So let me just, with one slide, tell you one of the things that the community learned, somehow the common learn about the question of thermalization, which is described in this slide. And so what we have in mind in this research is we deal with the isolated many-body quantum system. So here it is depicted as a one-dimensional model. And then what we do is we consider a portion of the system, A here, which we take to be much smaller than the whole system size. And so the idea is that we want to study thermalization in these sort of models, and this is possible when we divide it conceptually our system in a small part and the rest of the system, which is the effective path. And so this effective path must be much larger than the system of interest itself. And so the precise type of object that we look at is written here. So it's an expectation value of some time evolving wave function in the limit where we first take the system size to infinity, and then we look at what happens at very large times. And so what people, I mean, a lot of numerical works and theoretical research sort of chart a map of possible phenomenology. And what happens in the most in the typical case is that you will have some generic behavior which is described here. So if you're initially in a non-equilibrium state, so a pure state for the whole system, and then you let the system evolve according to some generic Hamiltonian, you will see that after some transient time, your finite regions, your local subsystems will equilibrate towards something which is described by a thermal ensemble. And so really you could, in this limit, you can predict the late time properties of your system based on a Gibbs ensemble. Sorry, just 1 second. All right. Okay, so this was, let's say this is the common lore in the community. And you see that here I have drawn some trash bins in the environment, because when we think of thermalization in this way, we really don't care about understanding what happens to the rest of the system. And mathematically, this is expressed by the fact that we essentially trace over the environment. So we are really only interested in a small portion of our system, and we think of thermalization by looking at that subsystem. But then we can do something else. So we can actually look at the environment, and we can imagine that in this scenario, we actually measure the entanglement of the free. And so not only we measure, but we keep track of the measurements in the environment. And so you can ask why should we do this? And I think that there are several reasons. But this type of say, protocol where we, on top of some unitary dynamics, we had some measurements, I think it's something that it's very common in the recent literature of many-body physics, where people have started to look at what happens when you combine unitary many-body dynamics with monitoring and measurements. And so the idea is that when you combine these two ingredients in a many-body settings, new non-equilibrium and universal phenomena may arise. And so it is interesting to investigate these kind of questions in a bit more detail. And also, this is motivated by more, ever evolving experimental possibilities, in particular by the physics of so-called NISQ devices, noise intermediate scale quantum devices, and more generally of quantum simulation platforms, where on top of having access to the real-time dynamics, we can really measure individual degrees of freedom, and then perhaps even perform feedback operations on the system, depending on the outcome. Okay, so in fact, this problem is very much was motivated by an actual experiment done at Caltech in the group of Manuel Andres. So this is taken from the plot, and so from these two works by the same people. So the first one is the experimental work. The second is a theoretical work that appeared at the same time. It's not supposed to happen. I see some flashing there.
Oh, that was the best move. Try to just get out and back in.
Make sure that people are still on.
They are, I think so. The call is still on. Sorry.
All right, so again, this is taken from these papers. First one experimental, and the second is the theoretical paper by the same group. And in this experiment, they really have a one-dimensional many-body system in a quantum simulation platforms of Rydberg atoms. And in this system, they are able to actually access individual atoms for measurements. And they really play this game. So they initialize the system in some trivial product state. They let it evolve according to the system Hamiltonian, which is not so important here, but just to, it's just important to bear in mind that this is a sufficiently generic Hamiltonian. And then at the end, they measure a part of the system which correspond to what we would think of as the environment. And then they record the outcome. And then they study what happens, and as I will explain in the next few slides. But so let me not talk about the actual experiment, which has some details that I don't want to get into, and let me focus on the second experiment, the theoretical paper by the same people, where they sort of take a simpler, slightly simpler point of view. And so the problem is the following. So again, we have so this picture you will see a lot of times by the end of the talk. Again, so with respect to the traditional setting that we have in formalization, not only we initialize the system in a simple product state and let it evolve, but at the end, instead of trashing this part of the system, we actually measure it and record the outcomes. And so if you imagine to repeat this experiment many times, what you will have is an ensembles of states where ZB corresponds to a string of outcomes. So if you have qubits here, this would correspond to a string of zeros and one. And for each string, you will have a probability telling you what is the probability that this string appears. And then you will have the corresponding wave function, which essentially in this picture lives on these two degrees of freedom. And so this is an ensemble. Why is this interesting? So first of all, this ensemble contains at least as much information as your reduced density matrix at some time. And it's very easy to see that if you consider this sum, so you average over the outcomes, the reduced density matrix that you get, you will actually end up with the reduced density matrix of your system. So this is, in a sense, gives you complete information about the thermal properties of your subsystem, but in fact, it gives you much more information. The reason why it gives you more information is because when you have a probability distribution, you're not just interested usually in the average, but you might wonder about higher moments and more refined properties. So the question that these people asked was, can we characterize this ensemble for generic Hamiltonians? Is there some dependence on the Hamiltonian? Perhaps we can use information of this distribution to, say, distinguish different dynamical cases. And are there universal features in this probability distribution? And so again, if we go back to the problem, one information that you cannot get from the reduced density matrix is the typical structure of the wave function that you get for a single individual measurement. So in other words, there are many ways in which different ensembles can give you the same average, but it might have a very different structure for the wave function for each individual outcome. Okay, so in that paper, they try to give a, to provide some initial typical understanding of what happens by looking at the case of chaotic or generic Hamiltonians. And in particular, they formulate this so-called K-design conjecture that I'm going to explain, which roughly works as follows. So first of all, let me introduce or call the notion of K-design, which is a concept that was originally introduced in quantum information theory. And so we usually people call it K-design any ensemble such that the expectation value of tensor product of states in this form match the expectation value over the Haar distribution. So for example, here, okay, so the point is the following. So we first define, so we have some collection of states, right? And then we can take the average of this tensor product here. And if this average coincides with the average that you would take on a Haar ensemble, then you say that this ensemble is a K-design. And so their conjecture was that if this dynamics is sufficiently chaotic, in a sense that one can make precise, then you should expect that at very late times, this ensemble becomes a K-design. So in other words, because the Haar distribution is the most chaotic and generic distribution that you can have, the claim is that if you're in the setting where you have a small part of the system and the rest which tends to infinity, then the system on its subsystem induces the most chaotic distribution possible. And this statement is not just valid at the level of reduced density matrix, but actually describes the whole probability distribution. Okay, so now what does chaotic and maximally chaotic means? So there are a few systems that you would obviously call maximally chaotic. One of them is a toy model where you do not take a Hamiltonian dynamics, but you actually take a quantum circle dynamics where these gates you take completely randomly. Or another type of dynamics that you would want to call completely chaotic is that where you start from an initial state, which is generic in the sense that it has it corresponds to an infinite temperature state, and then you evolve with some Hamiltonian that has no conservation laws. And so their claim is that when this happens, the full probability distribution is as generic as possible and resembles a hard random probability distribution. Okay, and they call this phenomenon deep thermalization. Now, they provide some numerics and some experimental evidence of this phenomenon. So here, let me just report their numerical experiment, which is unsurprisingly easier to understand. And so what they do here is they consider this average here. So they consider this average here. So they have their ensemble that they define in terms of these measurements. And it's defined as this average of this K tensor product. And they compare it against the one where they average over a random distribution. They call this quantity the delta of K. And so this quantity tells you how much your probability distribution differs from a hard random one, from one which is maximally chaotic.
That's not quite the Hamiltonian, is it? That's not the tuned reverse. You need some transfer speed.
Yes, of course. Sorry.
Okay.
This is a Y. This is supposed to be, I guess, a Y.
Yeah.
Of course, these are different. Yeah, sorry. Indeed. So and then they take this Hamiltonian where here there is a typo, and they check this Hamiltonian for generic values of the parameter where it is known that this Hamiltonian is non-integrable and the spectrum satisfies some typicality condition. And then they simply, I mean, all of this on a computer, they simulate this on a computer, they evolve this, and then they compute this difference. And you can see the result here. Of course, this is done by exact normalization, so they're limited to system size, and they can go up to 25 sites, where the subsystem size here is 3 qubits. So K equal to 1 would correspond to your typical thermalization problem. Because really this is, I mean, for K equal to 1, this is the reduced density matrix of the system. And as you see that there are darker and darker lines, this corresponds to larger system sizes. Because this is a statement in the thermodynamic limit, they only care that this delta K goes to 0 as the system size goes to infinity. And you see that as a function of time, this quantity goes to 0. So this is exponential, sorry, logarithmic scales, -1, -2, -3. So this tells you that this is 0. And this is, they see this numerically for K equal 1, 2, and 3, and therefore this is convincing numerical evidence that if, again, the Hamiltonian is chaotic enough, then you have this kind of deep thermalization. One point which is important here is that they start with initial state, which it corresponds to infinite temperature. Namely, that the expectation value of the Hamiltonian is 0, and it's the same that you would have in infinite temperature. Okay, so this is very nice, but if you want to go beyond numerics, this is very difficult. So you want to prove that this deep thermalization happens, this is very difficult. And so far, this has been proven only in some toy models for the chaotic dynamics provided by volume theory circuits that Bruno and Thomas introduced a few years ago by different groups, both in the US and in Europe. But then essentially if you go beyond this, then the best you can do is just numerics, and the numerics is limited by the system sizes. But beyond proving this, there are actually a lot of questions that people do not know the answer to, which is what happens now if we move away from infinite temperatures and perhaps we look at quenches from finite energy states. And maybe we also want to study explicit Hamiltonians away from maximum chaotic points. Okay, so our work is something very, very simple, where we start to understand some simple point which goes beyond this maximum chaotic case, which of course is something very special, and it is about free Fermions. So before that, let me just mention something else. which I don't remember, so maybe I will comment on this later. Okay, so again, I wanna keep the talk as simple as possible. So let me jump in directly to what we did exactly. So in our work, what we did was consider a very special Hamiltonian, which is obviously not chaotic at all. And this is the simplest Hamiltonian in a sense that you can imagine. So we consider now a free fermionic system on a chain of L sites, where essentially we just consider hopping between free fermions with the usual anti-commutation relations. And then what we do is we study a very simple quench problem where we initialize our system in a product state. So we focus on two-side shift invariant states because it's a little bit more general than simple product states, but we want something which is low entangled, following what we usually do in quantum quenches. All right, and then so let me recall a few very well-known facts. So this Hamiltonian is integrable, but in fact it's almost trivially diagonalized by Fourier transform. So you simply introduce this Fourier modes, and then your eigenstates will be written as product states of these Fourier modes. And also it is integrable in the traditional sense because it features an extensive number of local conservation laws, which you can these conservation laws are equivalent to the set of occupation numbers written here. Okay, so this is obviously something which is not maximal chaotic, and the question is what happens here. And even in the previous works that I mentioned, these non-interacting points were used as examples to say that the steep thermalization does not happen everywhere. But the message that I want to convey in this talk is that even in these very special Hamiltonians, and in fact I want to argue even beyond the intermediate case between chaotic and maximally integrable, we should expect that there is some universality and something interesting in this kind of ensembles. Okay, so first of all, in this model we immediately can tell that this K design conjecture will pay. And why is this the case? Well, because our initial state here is a product state, so it's a Gaussian state. And also the Hamiltonian is quadratic. So the dynamics at all times will remain within the manifold of Gaussian states. Okay, what is the Gaussian state? So a Gaussian state is a fermionic state which satisfies the theorem. So it's something very special. And because this is so special, we can engineer expectation values that will tell us immediately that this ensemble, this projected ensemble for this dynamics will not match a Haar random ensemble. So the trick is simple. So you take now this quantity. You see that if you have a state which satisfies weak theory, this quantity is identically zero. So even if you take absolute value and you take the power k and you take the expectation value, this is going to be zero. But if you take this quantity and you average over the Haar random ensemble over the whole Hilbert space, then this quantity is going to be different from zero. So this tells you that even if you start from a state which is infinite temperature, then there's no hope that this will give you a Haar random distribution. Okay, so what then the question is, what do you get? And do you get something interesting, or is this a super model dependent? Okay, so now let me walk you through the actual analysis that we did for this model. And I just want to stress that although this model is stupidly simple, as soon as you introduce measurements, then it becomes complicated to study. And this parallels recent studies on measurement-induced entanglement phase transitions, for example, which is a very popular topic in the recent literature, but also you have the same kind of problem. So there are a lot of works trying to study this kind of transition in fermions, but the point is that when you introduce measurements, the theory becomes, in a sense, effectively interacting, so it becomes complicated to study analytically. So even if the model is very simple, the analysis is not completely true.
Isn't this a little bit simpler because here you're measuring at the end?
Yes.
Rather than everywhere.
So of course there are simplification and we'll exploit them. So we can do things that you wouldn't be able to do in the most rare case. But in some sense, I mean, here really the more chaotic you are, the simpler the answer is. And as the more structure you add, the more complicated the answer might be. But now, of course, I'm going to explain there are a few simplifications. Okay, so the first simplification here is that because we're working with Gaussian states, all the information on the state is encoded in covariance matrices. But the covariance matrices is simply defined as a 2-point correlation function. And because the state satisfies the theorem, all the information on the state is in this L by L matrix. So because usually we need 2-to-PL coefficients to describe a state, again, this is immediately a very significant simplification. But the point is that because we need to study ensembles where you sum over 2 to the n outcomes, it still is complicated to provide analytical statements. And so what really this buys you is the possibility to do efficiently some numerics. Now, because again, the information is only encoded into this, the first simple observation is that we do not need to study the ensemble induced on wave functions, but it's enough to study ensemble induced on these covariance matrices. And so we really need to study just these higher moments defining terms of these matrices, which are again L by L. Okay, and then we can use this observation to set up some efficient numerics, which allows us at least to get to large system sizes and large times. And the numerics is based on 2 things. So first of all, because as you said, because we measure only at the end, the dynamics is trivial up to the measurement. But then even the measurement does not spoil the Gaussian condition. And so when we perform measurements, even after the measurement, the state remains Gaussian. In practice, we can even find the covariance matrix of the state after the measurement. So here there is a simple formula on how the covariance matrix transform if you measure a fermion at some position L. So here we measure this density, which really means we do a projective measurement on a single site. We look whether the fermion is there or not. And after this measurement, you know, this is how the covariance matrix transforms. This depends on the number Z, which is either 0 or 1. So the fermion is there or not. And you can actually compute the probability distribution on this. So this is for a single site, but this formula generalizes for a string of sites. And so because these quantities are efficient to evaluate, you can set up a Monte Carlo numerical scheme, where again, so the steps are first, you evolve up to time t. Then when you're here, you essentially simulate the sampling. You start with some arbitrary string, and then you crank in the logic of the metropolis. So you pick one side, you flip it with some probability, and then you accept or not, depending on the usual rules. But it is crucial that in order to compute these probabilities, it is crucial that this is efficient in terms of covariance matrix. And so this allows us to provide reliable numerics for, say, 400 sites and times equal to 100. Okay, so what we do then using all of this is essentially 2 results. So the first one is we put forward sort of a generalized ETH eigenstate normalization hypothesis, which I'm going to explain for this projected ensemble. And then the second one is that we, based on this hypothesis, we derive a complete characterization of this ensemble for infinite temperature states. And the interesting physical message is that we recover some universal behavior even in this stupidly simple types of Hamiltonian. Okay, so let me start with the first point. Okay, so here let me start with the conjecture. So the conjecture is that here when we okay, so in this process we start with some initial state, we evolve it, and then we take measurements. And our conjecture is that it doesn't really matter if you know or not the details of your initial state. The only thing that matters is that you know the conservation laws on the initial state. So in other words, it only matters if you know the occupation number n of k. Now for this initial state, they look like this. And so our claim is that if you know these, then you can reproduce this ensemble. Now for k equal to 1, this is well known. It's essentially the generalized Gibbs ensemble hypothesis in disguise. But our claim, which again it's very natural, but in principle non-trivial, that this is enough also to reproduce the whole ensemble. And so how do we test this idea? So what we do is we take now a state which is built as a Fock state in momentum space, where these k's are distributed according to the n of k of the initial state. And then we sample, without any dynamics, we sample the state in the same way. So here we have a dynamical process, here we don't, we have a single eigenstate and we sample from it. Again, so this is a very strong statement because it tells you that these local absorption laws only, constrain the whole ensemble and all higher modes. So we compare the results from the two by computing this delta of k, which is reminiscent to the one that we saw in the paper by Ender's group. And this is the numerical result that we get. So first of all, here we see that we have a slow power law decay of these objects, which is expected. So for k equal to 1, this is true, and you can compute analytically, but not surprisingly, you see the same kind of slow power law decay for higher moments. But they, in log scale, they are convincingly all going to 0. Okay, so so this is just one example of our data, but all the examples that we tried, they convincingly show that this type of please.
So this is something I noticed in the paper you showed me, from the paper by the others.
Yeah.
That the larger k, the higher these, these curves are.
Yes. Yeah, this is a very good observation. So they in that paper they do not. They take this a phenomenological observation, but in one of these subsequent paper where they study this in synthetic models of quantum circuits, they're actually, they can justify this, that in general you should expect that the decay is lower for higher k.
Okay.
So
this limits the depth of this deep thermalization.
So it tells you that if you wanna have something that resembles the Haar ensemble to higher modes.
Larger k don't get touched.
Exactly. But this is this is deep because for quantum information people, it is very important to provide protocols that give you distribution that resemble the Haar ensemble. And now there is this conjecture that if you have a quantum circuit, then if you want to get to something which mimics the ensemble up to moment k, then your time should be proportional to k. This is one conjecture. So that if you want something that really resembles the Haar ensemble and you want to play with random circuits, then you want to. This is difficult to do. And so yeah, you sort of expect that this becomes more complicated for us. And we find the same for free fermions. Right. And so by analogy, we call this the deep generalized Gaussian ensemble. And again, for k equal to 1, this is nothing but the well-known GG that was popularized by Enrico in 2007. Okay, so then we so this is sort of again. So again, let me stress that this is a conjecture for us, and we're not able to prove this. And we think this might be possible, but it's not true. So since there are a lot of very smart people here, this could be one interesting problem to look at. And also, so differently from the case of maximally chaotic dynamics, it seems there is no natural toy model for this, because if you take, for example, one unitary circuits at the 3 points, they become swaps, so trivial, and so that is not a good model. So another possibility could be to find an even simpler model where it's okay, but now we accept this hypothesis and then we start to derive consequences. And the first thing is what happens when you have infinite temperature initial states. So in this limit, you might expect that something universal happens just by a trivial observation that if you start with something which is infinite, temperature, at very light times, your density matrix will be the identity, so completely structureless. There is no information on the Hamiltonian. So is the same true for higher moments, or will some information be retained on the details of the Hamiltonian? And again, for the Haar case, we know this does not happen, but there is this seemingly emerging conflict that here some information must be retained because this cannot be the Haar random ensemble. And so the solution is that this indeed is a universal ensemble, which is called the random Gaussian ensemble, which was, again, recently popularized by different groups. The first paper in the recent literature seems to be one connected to the SYK model, but then also Marcus Rigo, Eugenio Bianchi, and other people, and then we also worked on this, which now I'm going to explain. So essentially, the idea is very simple, and this kind of ensemble is realized when you start from some target Gaussian initial state, and then you apply to it a random unitary, but this random unitary is chosen to be quadratic. So at the end, you have some random state, which is Gaussian by construction, but otherwise completely structureless. And you can show that for this kind of ensemble, this distribution induces a distribution of the level of covariance matrices, which is defined in this way. So it's the ensemble of covariance matrices which are conjugated by a unitary U, which is drawn from Haar invariant measure. And so I call this a universal measure because it doesn't depend on anything, on any detail within Hamiltonian, if not by the fact that this is quadratic. And so let me just say a few words about this ensemble. So this is a legitimate ensemble of random states, and the same way as you can, compute things for Haar random states, you can also compute and characterize this ensemble. Although this is very natural, very simple, somehow, people only started to define this and study this in the past few years. So for example, you can compute the page curve on this ensemble, which is this line blue. It's the dotted line in the thermodynamic limit, whereas the dotted line here is the one on Haar random states. So let me define what is the page curve. So when you have an ensemble of random states defined on some set A, B, imagine you have some pure state defined on this little thing. You can bipartite into two, and then you can ask what is the typical entanglement of a state in this ensemble. So this is called the page curve. It has connections to high energy theory. And for Haar random states, this has been known for 70 years. And it's something very simple. So essentially, this is the curve as you vary the relative length of A with respect to the whole system size. And for Haar random states in the thermodynamic limit, you have something which is this, so maximum entangled state. And what I'm saying here is that these random Gaussian states are less entangled. You see that there is a gap, but they're still volume law entangled. So they're quite complicated. So here we plot the intensive bipartite entanglement. Okay, and so people studied a few properties of this. Again, the thing that I want to stress is that this ensemble is an ensemble of quadratic Gaussian states, but it's not particularly simpler to study than the Haar random ensemble. Because again, so you're constrained something which would otherwise be completely unconstrained. And I mean, in the thermodynamic limit, the page curve for the Haar random case is trivial. It's a constant slope, whereas it becomes non-trivial for the case of random Gaussian states. Okay, so now we, based on our generalized ETH, we are actually able to prove that for infinite temperature, and so yeah, please.
I go start on the.
Yeah.
So these are volume law because that blue curve, the height scales as n. You divide it by n.
Exactly. So here it's probably difficult to
Not
read.
square root of n, just n.
Yes, this is s divided by n.
That's it.
Based on this conjecture, then we're actually able to prove that for typical initial states, meaning middle of the spectrum, so maximal entropy, Boltzmann entropy, we get this random Gaussian ensemble. So there is just one caveat, and the caveat is that in fact it's not exactly that, because our Hamiltonian has some global symmetry, which is a time reversal symmetry, and so as it is traditional in random energy theory, we have to enforce this global constraint, and so the actual ensemble looks a little different, but it's more than the same thing. So up to some fixed matrices, it's essentially a conjugation with respect to a matrix which is chosen. It's Haar invariant in the orthogonal group, not the unitary group. So, but this is just so essentially we get something universal. Okay, so with this, I think I am done. So let me just, okay, so sorry. So then we numerically, again, we test this conjecture. And of course, everything should be consistent. So indeed, we find that this holds. Again, in the first panel, we plot this difference, which seems to go to 0 with the same features that higher K needs higher, longer time. But then we also look at the bipartite entanglement entropy of the subsystem A. Now here, I want to make it clear that this A1, A2 are a bipartition of the small system. So we're looking at the average entanglement for the small subsystem because we always assume that the rest of the system is infinity. And the blue curves are the dynamics. Then there are some continuous and dashed curves in black, which are on top of them, showing that we have excellent agreement. And then we also plot some red curves to show that the unconstrained ensemble does not match these predictions. And so we'll just say that everything is consistent and seems to be according to what we say. Okay, so now finally, just the outlook. So in a sense, this work is a little bit more about questions than answers, but we do clarify a few things. So the first one is that I think we provide evidence that it makes sense to define a deep generalized Gibbs ensemble, meaning that it seems that local conservation laws constrain not just the first moments of distribution, but the whole, higher cumulants as well. And also, I think what is nice here is that it shows that these ensembles can show universality even beyond the maximality of the case. But then they raise this, this work raises a lot of questions. Again, so the first one, which is obvious, is can we make can we prove our conjectures, or is this too difficult, or can we find simpler models where this can be done? Then, a question which was really in this previous paper is what happens when we now look at finite, initial states with some finite energy. And in this paper, they provide some conjecture for it, which is so they propose a so-called Scrooge ensemble, Scrooge as in the famous book. But we think that conjecture it cannot hold exactly for finite subsystems. It probably holds in some limits. But anyway, so in any case, they only provide evidence. It would be nice to have some deeper understanding at this point. And finally, I think it's very intriguing to ask what happens when you're in between. So for example, even if you take some Bethe-Ansatz integral model here, it's very confusing because on the one hand, you lose the Gaussian structure. On the other hand, you have conservation laws. So then, what do you get? Do you get something universal, or even in the infinite temperature sector, you get something which is highly model dependent? And of course, you can also ask what happens when you have FDL systems or other type of dynamical phases. Okay, and so with this, I conclude and I thank you for your attention.